Hello and welcome back to Calculus2 section 6.7 on surface area of revolution. So previous two sections for this class are missing because we were outside. It was nice. Today we're back in the freezer over here to continue with the stream and lecture notes and everything. So last class, which was outside, so there is no lecture for it, we said that the length of curve is given by integral a to b of square root of 1 plus f prime squared, derivative squared, dx. And that one gave us the length of the curve. What we are going to do today in 6.7 is we are going to rotate this length in space and calculate the surface area of the object. So you see, when you have some kind of a curve f of x, we can calculate its length using the formula that we learned last class. But now if I decide to rotate that curve on the x-axis, it is going to go like that and create the shape like this. So now that L is rotated along this outer circle, so multiplying this L by 2 pi and the x and the f of x, we can get the area of the outside. So we are calculating the area on the outside. We're not calculating volume. So the formula for today is area, well, we use S, surface area. I don't know why I use S, so whatever. 2 pi integral a to b of f of x times the square root of 1 plus f prime squared of x dx. And the y version, same formula, 2 pi c to d of f of y square root of 1 plus f prime squared of y. I don't want this to look like 12 squared y dy. So these are the formulas for surface area. And the top one rotates around x for red, and the bottom one rotates on the y. So let's take a look at the simplest example here. Say cone. I'm going to rotate cone on y-axis. I mean, rotate the line segment on y-axis to make up a cone. So, and we will use the blue formula because it rotates on y. So if I have a function like this, let's say, this goes out to 2, and it goes up to 5. And if I rotate this on y-axis, it will create another side over here. It would create this circle on the bottom, and it creates a cone. We can write out y equals negative 5/2 x plus 5 as our linear line. This function goes down and because it goes down, we can calculate the slope by saying it's negative 5/2 because it goes 5 in y and 2 in x direction, but it drops, so it's negative. And the y-intercept is 5. So that's what we have. And now we go and say, yeah, that's all good. So now we, since we are rotating on y, we have to use dy, which means we need x as a function of y, which means we need to flip this. So that's the line of thinking. You see, your y rotation gives you the dy integral, and because it's a dy integral, the whole thing has to be in terms of y. So you look at the picture, you know it's a y rotation, and then y gives dy, dy gives the functions in terms of y. This one is given in terms of x, so we have to flip it. So that's how we know we need to flip. So we flip. We say y minus 5 is equal to negative 5 halves x. We are solving for x, right? So I want to solve for x. I just multiply both sides by negative 2/5. And we get negative 2/5y plus 2, because 5 and 5 would cancel, and then it's equal to x. So my f of y is equal to negative 2/5 y plus 2. That's what we have. Yes. So I have the function. Now we need its derivative to plug into the formula, and its derivative is negative 2/5. So I can now set up my surface area integral as 2 pi integral, and now I need y limits because this function is in terms of y, and that's going to be 0 to 5. Remember, we are using dy. I can draw dy over here, right? If I draw dy as this horizontal representative rectangle, you see that the lowest that dy can go is 0, and the highest it goes is at 5. So 0 to 5 are the y limits. And the next thing is we put the function as is. The function is negative 2/5 y plus 2 times the square root of 1 plus derivative squared. That's negative 2/5 squared dy. And all we need to do is to compute this. So we have 2/5 integral 0 to 5, negative 2/5 plus 2, negative 2/5 y plus 2. Now over here we have 4/25. This is 25/25, so 29/25 the y. So that's when you add fractions. So when you square negative 2, you get positive 4. So 4/25 when you square. And because your denominator is 25, then 1 becomes 25/25. And then 25/25 plus 4/25 is 29/25. Now that's a constant. And oh, I forgot to factor out. What I wanted to factor out here is a 2 from the first parenthesis. So this is a 1 and a 1. Oops. There we go. Much better. So now kick all of the constants outside. We have 4 pi times square root of 29, everything divided by 5, because the square root of 25 is 5. So we kick out all of the numbers, and we are only left with integrating negative 1/5 y plus 1 dy. So this is what we have as the integral. So we kick the numbers out. When we integrate, so we have our 4 pi root 29 divided by 5. Integrate here. It's going to be negative 1 over 10 y squared plus y, computed from 0 to 5. And we plug in values. 4 pi square root of 29 divided by 5. And now when I plug, I don't have to plug in 0, I just need to plug in 5s. I have negative 25 over 10 plus 5. 5 over 1, 50 over 10, 25 over 10. Okay, 25, so 5 pi square root of 29 over 5. And then this is 25 over 10. These guys will cancel to a 5. Then the 5 cancels with a 10 for a 2. Then 2 cancels with a 4 for a 2. And the answer is 2 pi root 29 units squared. Yeah.
I know this is like, it's like basic whatever, but it just really confuses me. When we're actually computing with the limits, like, say instead of 0, it was 1, like, we have to actually, like...
You would have to have another term over here, the same term like this. So you would have to plug in 1 in each one of these and subtract it.
Okay.
Because the formula for computing these limits, integral a to b, let's do it in blood, integral a to b of f of x dx is the antiderivative f of x computed from a to b. That is actually equivalent to this step here. And then it will be f of b minus f of a. Now, this over here is just f of b because a was a 0, so I omitted writing minus 0 because when you plug in 0 into... Oh, thank you. When you plug in 0 into y's, they're just 0. You are not always going to omit 0. E to the 0 is 1. And cosine of a 0 is 1 as well. So you're not always ignoring zeros. But when you have polynomials, you have a sine, you have a tangent, you are omitting zeros because they're going to give you 0 in the calculation. So this practice formula, right, to calculate this thing is going to be that extra homework I posted, 5.2, to practice the red formula for definite integrals.
I have a question on what we just did.
Yeah. Mm-hmm.
Does the answer that you got also include the surface area of the circle on the bottom of it?
No.
Okay.
You have to separate it. You have to calculate that separately. This is only the face, only what you can, when you put the object down, only what you can see on the outside.
Okay.
So in this case, the whole red area over here, all of this stuff, right? That's all given on the, that's all calculated by the integral.
But you can figure out the top and the bottom and then add them, right?
Yeah, because the area of the bottom is just pi r squared, right? It's just a circle, pi r squared. So it's very easy to If you have a circle on the top, circle on the bottom, right? Over here is for this bottle, right? I have a circle over here. I can measure the width, which is diameter, cut it in half for the radius squared times pi. Same here, measure the size of the diameter. You use those, what's it called?
Micrometer.
Yes, thank you. You put it here, and it tells you the width, right? At its fattest, because it's a circle. And then you cut that in half, gives you radius. Radius squared times pi will give you the area. And then you just add that if you want everything. But generally, we don't care about this because you don't do the design.
I can just like imagine a homework problem being like, what's the total surface area if it was a solid object?
Perfect.
Like,
yeah, why not?
You do the whole thing correct, and you're like, what the hell am I doing wrong? And it's like, oh, you didn't add these
extra fees. Yes, so this does not include. So over here, I'll write it in blood. Circle not included. There we go. Circle not included. So we know that it's only the surface area of the wrapping around, so for the cone. So technically the part of the cone, if it's ice cream cone, the part of the cone that would touch with your hand, right? The circle is where the ice cream sits. You can't touch that one. I'm going to pick one more example from the textbook homework part. Work one more example, and then we're going to hit the break. I'm going to borrow the book, see what's...
This is not the same.
It doesn't matter. It's the book is the book. We're just going to take...
I don't know where this section is.
So, we are going to go look for...
It goes right into chapter 7 after that.
Shells, cylindrical shells, work energy. Has to be, well, we can always look in the table of contents, or we can look in the...
This is like the same textbook, but it's the Rutgers version.
That's okay.
Telling you about.
Application area potential. So it's in 8.1 surface area. So 470. It has to be somewhere. Right? It's calculus. It has to be somewhere.
This one is like 10 years old, so I can imagine the order and everything.
It's just different order. It's just, it has to contain the same calculus. So there it is, and there's the formula we just covered, boxed on 470. Approximate the length of the curve. Surface area. There we go. So, well, they do say e to the negative x 0 to 1. Why not? Y equals e to the negative x 0 to 1 around x-axis. So previous integral we did was the rotation on y. Now we're just going to do rotation on x. Great. If you want to graph this and see what it looks like, you can quickly graph this function like that. That's your e to the negative x. And then chop it up at 1. So the bottom piece, because you're rotating on x-axis, the bottom piece would come in from here, and then you would create this object like that. These curves are not straight lines on the side, therefore this is not like a cone that it's cut off or anything. It is actually, might look like a termite nest or something like that. I don't know. So, sideways, obviously. So we can immediately go and calculate the surface area as 2 pi integral 0 to 1. So your a and b are given, right? So you just put them in, 0 to 1. And we have e to the negative x times the square root of 1 plus, and now you need the derivative of e to the x. So y prime is going to be negative e to the negative x. So we over here have to say negative e to the negative x, and we need to square that for our integral. And there we go. So let's see if we can integrate this. So 2 pi integral 0 to 1 e to the negative x square root of 1 plus, when you square, this minus goes away, and you have e to the negative 2x dx over here. And now we need to integrate this somehow. So I see the problem with picking random problems like that is that we don't have all the integration techniques, because they had integration techniques before they introduced. So all right, so what do we do here? If we want the u sub on this one, if we want the u sub on this one, then we need e to the negative 2x in front, and we don't have it. I don't think we'll be able to integrate this, actually. U equals 1 plus e to the negative 2x, then du is going to be negative 2 e to the negative 2x dx. And see, I don't have a negative 2x over here for u sub. So we can't use u substitution, in which case that means that we cannot integrate this because we are not there yet. Well, at least we set it up. Well, guys, the entire chapter 8 is there for us to learn different methods of integration, right? So use chapter 8 or computer to integrate. And we can pick another example. I'm going to log on real quick to the book and pick up another example, something from homework that we definitely can do. Also, guys, I did mention this last class. I'm just going to say it one more time. When you are reading your book, if you see that blue T will ask you to use computer to integrate, because they again pick the values and functions that you cannot integrate yet, or they cannot be integrated at all, and the software is using what is known as numerical integration. We are going to learn that as well in chapter 8. You already seen some numerical integration in chapter 5, like 5.1, but that one is not as good as the things that we are going to learn eventually. So we don't have to panic yet about that stuff. All right, so let's take a look at one more second to get into the book. Three more seconds over here. All right, so section on surface area, and we are going to work on, let's say, we can work on, let's say, square root of 5x minus x squared. So y is equal to the square root of 5x minus x squared on interval 1 to 4, and it rotates around x. All right, so previous problem we just set up. Now this over here, we are going to set up the same way and solve all the way. So first order of business is to find the derivative of the function, because we need to plug that in that square root in the formula. So now we have to take the derivative of what we see. That's going to be divided by 2 square root of 5x minus x squared, and then 5 minus 2x on top. So that's the derivative of the function. The derivative of a square root of x is 1 over 2 root x. And if you have something else other than x in the root, then its derivative goes on top. So that's from Calculus 1 chain rule is the method we use to find the derivative here. And now we'll just find the surface area because we have all of the ingredients for our soup. Right? We have 2 pi, we have 1 to 4. Now we have the function as is, which is 5x minus x squared times the square root of 1 plus, and then we have this 5 minus 2x divided by 2 times the square root of 5x minus x squared, everything squared, dx. Are you regretting it yet? No. It's not gonna be the problem, right? We're just gonna plow through this. Integral 1 to 4, square root of 5x minus x squared, and then the square root of 1 plus 5 minus 2x squared on top. The bottom kills the, that's a 4 on the bottom. 2 squared is 4. And the bottom just kills the square root. So that's the easy part. And now we use the algebra formula. Square root of a times square root of b is the square root of ab. So these two separate square roots are going to multiply their arguments. And when you multiply everything by 5x minus x squared, you can see that it just cancels in the second one. So we lose the double fraction and all that stuff, which is awesome. So 2 pi integral 1 to 4, and now it's just one big square root. Now, guys, this is over here 1 unit, and that multiplies into 1, and then multiplies into this, right? So it distributes over both. So I use it as a unit. So when I multiply it by 1, I just get 5x minus x squared. And then this plus is the plus that goes there. I can actually connect them using here. So that plus is this plus. And then now they cancel. This one and this one cancel completely. So all you're left with is the numerator divided by 4. So you have this 5 minus 2x everything squared divided by 4 dx. And there are multiple ways you can do this. Obviously, we have to square this one. So 2 pi integral 1 to 4 square root of 5x minus x squared. You can say over 1 plus. This is going to be over 4. We'll have to do the common denominator to put them together. So now 5 squared is 25 minus the 2ab. So 5 times 2 times 2. So 5 times 2 is 10 times 2 is 20x plus 4x squared dx. 2 pi integral 1 to 4. Now this first one needs to be over 4 to have the common denominator for the second one. So when you do over 4, right, you have to multiply top and bottom by 4 to get the common denominator. That's 20x minus 4x squared over 4 plus 25 minus 20x plus 4x squared over 4 dx. And now 20x, negative 20x, negative 4x squared, positive 4x squared. We are left with So these are all gone. We are left with 2 pi integral 1 to 4 of square root of 25 over 4 dx. Awesome. Square root of 25 is 5, square root of 4 is, so this is 2 pi, and then you just have 5 over 2 integral of dx, 1 to 4. 2 and 2 will cancel. So we have 5 pi integral of this is x computed from 1 to 4. And now we have 5 pi 4 minus 1, which gives us 15 pi as the answer here. 15 pi units squared, whether it's inches squared or centimeters squared or whatever, is the surface area of the shape that we get when we multiply this. Was a lot of algebra. So what was, when you look at a problem like this, and you realize that your calculus is, 3% of all of this stuff, you have to memorize the formula, and that's your Calc 2. That's the only thing that it's Calc 2. You memorizing one formula. So if you know the surface area of revolution formula, you know your Calc 2. If you are able to integrate at the end, which is going from here to there, right? Then you know your Calc 1. Everything else was just shoveling algebra. It's a lot of it, right? Knowing the formula to combine the roots and all of that kind of stuff.
Where'd you get that x from at the end?
The what?
Where'd you get the x from at the end? Like right after the last dx?
Over here?
Right after that? Yeah.
When I integrate 1, you get x. Integral of 1 is x. Integral of a constant. Integral of cx is, integral of c is cx. So you get when you integrate. That was the 4.9.
Wait, is it the c that turns into x, or is it the d?
1, because that's the usual one that confuses everyone. So when you have integral of dx, you can write that as integral of 1 dx. You can write 1 as x to the 0 dx. And then when you use the formula x to the n plus 1 over n plus 1, because this is x to the 0, you get x to the 0 plus 1 divided by 0 plus 1 plus c, which is x plus c. That's why integral of dx turns out to be x. And if you have definite integrals with limits, then you don't have plus c, you put the line and this thing. Ta-da! So that's 6.6. We're going to go the break. When we come back from the break, we are going to continue and do the last section. Physics, we'll have to do a few things. There's going to be integrals and so on. All right.